Okay, so I'm going to look at Ansys and modelling piezoelectric materials. You can use this sheet along with going through the model. We're going to do a 3D model, and the key point is this is the important equation for a piezoelectric element. It's the coupled field constitutive equation. So it relates the stress T with the dielectric displacement D. It's the sort of charge density, coulombs per meter cubed, that's generated with the strain S and the electric field E. And to do this in the element, it needs these materials properties in a way: the stiffness of the material, so the stiffness matrix C, and you see the superscript E, and that means it's the stiffness at constant field, and that's the short circuit stiffness. And the reason why that's important is that a piezoelectric develops a voltage in response to a stress, and so you have a Hookean strain, but also you have a piezoelectric strain. So depending on whether it's short circuit or open circuit, you're going to get different stiffnesses. In this case, we'll use this stiffness matrix. We also need the permittivity, but again, you can see it's a superscript S, and that means it's a constant strain. So it's a clamped permittivity. And again, it has a different permittivity if it's unclamped, which is at constant stress. Again, you just need to be careful, and I'll try and show that when we input the properties. And here we have the E, which is the piezoelectric charge coefficient. So it's the charge density, coulombs per meter squared, per unit strain. So it's the piezoelectric charge coefficient. So again, there's a D coefficient, which is the voltage coefficient. But again, we're going to use that value. And I'll try and explain that there are various compliances, or the D coefficients instead of the E coefficients for the piezos that you can input into Ansys as we go through. But let's put these into Ansys first before we generate a model. So I'm on UniApps, and we're going to use Ansys 2020 APDL. So it's mechanical. It's the slightly, it's not the desktop, so it's APDL 2020. So let's just sort out the window, because I always get it a slightly different size to how I want it. So we have the basic front end. So I just basically go through preferences, preprocessor, load your element in, load your materials properties, solution, build your model, apply your loads, solve it, and then general post-proc to look at the actual results. So preferences, well, we're going to do a structural model, obviously, because we're going to look at displacements in response to an electric field. But also we can see here there's an electric element, obviously, because we're going to get voltages or electric fields applied to the material. Preprocessor, we can just go through. Well, we need to add an element type. We need to tell Ansys that we want to do really that constitutive equation that I just went through. So we need to add that right element. So we add an element. So you add an element, and there's a whole host: structural, thermal. So if we go down, it's a coupled field. So coupled field means that the piezoelectric and the mechanical aspects are coupled. So if you apply a stress to a piezoelectric, you'll get a Hookean strain based on the Young's modulus, but you also develop a voltage. And what does a piezoelectric do in response to a electric field and a voltage? It strains, so it'll offset that Hookean strain. So there's a coupling between those two. We're going to use a 3D element. We're just going to model a square shape. So we'll just use a scalar brick. So solid 98 is for tetrahedral. If it's obviously a more if you want to get a better mesh fit, but we're only going to do a square, so this is okay. Options. So we got degrees of freedom. U is potential, voltage. You can, if you want, maybe reduce it, but I'm just going to keep it to the defaults because it doesn't really make much difference. So here we have our element. And that's that. We're not going to add anything else. No real constants. It's not plane stress or plane strain. So now we're going to add our materials properties. So we can add a material model. So it's just basically material number 1. And so we need to first input our structural element. So we want to put in that stiffness matrix. So it's nothing non-linear, nothing fancy. Linear element, an elastic element. And now we're faced with 3 options: isotropic, which means the same stiffness in all directions; orthotropic, stiffness in X, Y, and Z; or anisotropic, where we get stiffnesses in all directions. And that's really what we're going to need to put in. And then we're faced with this mass of D numbers, which are basically the C coefficients in that 6x6 matrix. So it's worth just thinking about that. So in an anisotropic material, so we have our anisotropic material, and basically it's polarized and active in one particular direction, and so it's polarized and active in the Z direction. And what that means is in most materials it's going to have different properties in that Z direction, that 3 direction, compared to the X and Y direction. So it's going to have an anisotropic stiffness, so we need to define it by this 6x6 matrix. And there's relationships between, there's a symmetry element, so X and Y are the same, so you can see that C11 is the same as C22, for example, and there's also a sort of symmetry with the shear coefficients C44 and C55. There's a slight issue with Ansys in that this is C66 here, but this is obviously C66, but these two are just in the wrong positions, and so you have to make sure that C66 goes in C44 in the matrix and that C44 goes in C66. It's a slight idiosyncrasy of Ansys, but it's just because Ansys is trying to be an element and a model for all sorts of things, and so you just need to be wary of doing that. The differences are actually quite small. C66 here is only 2.35 compares to 2.3, but it's worth doing correctly and make sure that you put it in the right one. So I have some data here. So these are the stiffness coefficients at constant fields at 10 to the 10 pascals. So I got this from a paper. There's plenty of them on the internet. Sensors and Actuators, volume 118, page 117, 2005. So let's put that in. So C11 is 12.6 e to the 10. C12 is 7.95 e to the 10. C13 is 8.41 e to the 10. C14 and 15 and 16 are 0. C22 is the same as C11 because there's an XY sort of symmetry, but not with Z obviously. The polling direction, so 12.6. C23 is the same as C13, 841 e to the 10. That's 0, 0, 0. C33 is there sort of on its own because that's the polarization direction where the material is active. C34 is 0, 0. C44 is obviously then C66 as I mentioned earlier. So it's 2.35 e to the 10. C55 is C44 because of symmetry. And C66 is C44 likewise. So there's always a slight window issue with Ansys here, especially on desktop. So yeah, just check. So I've got that in. That looks good. That's fine. So I've got my stiffness matrix in. So that's the C. So remember, I also need the permittivity. So it's not permeability, remember, that's magnetic. So it's relative permittivity, and it's not constant. It's different in X, Y, and Z. So we choose orthotropic as our stiffness matrix, and I have data, again I found from the literature, 1700 in X, it's the same in Y, and surprise surprise it'll be a different permittivity in the polarization direction, the Z direction or the 3 direction. In the piezoelectric, let's just go through the matrix. So I have this matrix here, so let's just go through. So this is my piezoelectric matrix. I've got it in this E form, which is remember the piezoelectric charge coefficient. So it's the charge density per unit strain. So the units are coulombs per meter squared. So I have E13, E33. So this is the charge density by applying a load in the poling direction. These are the charge densities as a result of poling, applying a load in the X and Y directions, and these are shear coefficients as well. So let's put those in. So in E13 minus 6.5 coulombs per meter squared, sorry, minus 6.5, 23.3, 17 and 17. So I've got my permittivity matrix added into the model. So this should be good. So I've got my stiffness matrix, I've got my permittivity matrix and my piezoelectric matrix. So I can almost save that as my materials properties. So save that as, so put that on my files, just in case this doesn't work. I'm sure it will. PZT5H 2021 B. Let's call it test. Okay, so I've got the materials properties in my model. So now let's try and create a geometry and then apply an electric field and see if I get the right answer. So if I look at, so I've got now pre-processing, I've done my materials properties. So if I got my modeling now and I create a volume, and I'm going to create just a block, a very simple shape by some dimensions in X and Y. And it seems a bit strange, but it just makes the mathematics a little bit easier when we test if this is doing the right sort of thing. So I'm going to make a 1 meter by 1 meter by 1 meter block of this piezoelectric material PZT5H. So it's a huge block of 1 meter by 1 meter by 1 meter, and I'll explain that when I go through the calculation when we see the results. So I've got my material now, which has material properties 1, which are those properties that I put in. So let's mesh it. So we've got a very simple geometry, so we can just use the mesh tool with smart size and mesh it. So we'll just mesh the geometry, and it says which geometries, what you want to do. It's giving me some warnings that I haven't got any mid nodes, but I'm not worried too much about that. So I'm going to just pick all the volumes. There's only just this, and they're going to mesh it, and there you have a very simple mesh. And in reality, I think this would work if it's just one element, let alone this sort of structure here. But this will be more than fine. Good. So now I need to apply a voltage, and I need to apply some symmetry to my model. So the main thing, well, one of the main things is to then how do we apply a voltage? And very often we just paint an electrode. You have some sort of conductive electrode on the top and bottom of the material, and so you make an electrical connection, and so we have to do the equivalent. So let's just change the way this is ordered, and then just plot, rather than the elements, plot the nodes, which is just the nodes. You can see now, so here's my Z direction, So remember that the way that I put the matrix in, the stiffness and piezoelectric and the permittivity matrix, is that the active direction is the Z direction, the 3 direction. So what I want is an electrode on the top, so all along the nodes along here, and electrodes all along the bottom. So I've plotted the nodes, and so I want to select some entities, and basically I want to make all the nodes at the top at the same voltage. So I select the entities, and I want to select nodes by picking, okay, and the way I'm going to do that, by drawing a box, because I've got a very simple geometry here. So basically by doing that, I'm selecting all the nodes along the top face of the model, and I click on OK. So now I've just basically I've just selected these upper nodes, and if I can just replot, you can see all the others have disappeared because I've selected these. So those are all the nodes on the top face of my piezoelectric element. And then what I'm going to do, I'm going to write a bit of code or command. That's not a code. CP 1 volt and all. And really what this means is basically it says coupled set 1. So this first set, which is my first electrode, in the degree of freedom of voltage, couple them all together. That's good, and they all turn green. So all those nodes are all in the same, going to be at the same voltage, and that's the equivalent of painting a conductive electrode on it. And then if I select everything, which is select everything in the model now again, and I plot the nodes again, plot, replot, select everything, sorry, plot, replot. Oh, what have I done? Oh, I need to zoom out. Yeah, so here you go on my couple set. All the nodes at the top are in this couple set. Now I need to do the same for the base. Oh, that's right. So the bottom electrode. So I've done that for the top. So I need to select another coupled set at the top. So it's at the bottom. So select entities. Again, all the nodes. OK in a box. You can do it by location. So as you get better, you can just put in some coordinates. It's a lot easier. So I've selected all those, and I just do plot, replot, just to, yeah, there they go. And then I make this the second set. So CP, couple set 2 volt in the degree of freedom voltage, couple all of them. So again, there's my second electrode, and then just remember to select everything again, and then replot. Now I have an upper and lower electrode, and if I do it on an angle, you can probably see that better. Yeah, so that's good. And it's sometimes of interest just to do CP list afterwards. So it lists your couple sets. So I have 2 sets, 1 and 2. So you can see couple set 1 are these nodes, and couple set 2 are the other nodes. And the first node in a couple list is the master nodes. So 17 and 1 are the master nodes. So all these other nodes will follow 17. All these other nodes will follow 1. So if I apply a voltage to 1 or 17, all the others will follow. That's good. So I think that's good. So we've got an electrode on the top and bottom. We've got the materials properties on. Let's just plot areas. So the last thing that I think what we need to do is I could then try and solve this, but it wouldn't solve very well because it hasn't got a mechanical boundary condition. So there's a symmetry associated with the structure. You need some mechanical boundary condition as well. And what's easy to do in this case is imagine this as a quarter of a larger piece of PZT, and so what I can do is apply symmetry on this face, on this face, on this face, and that's one way to do it. You could cut it down the middle, and apply some constraints in X, Y, and Z, but I think it's a lot easier in this case because we're just trying to learn how to use the piezoelectric elements to put symmetry on the three faces and imagine it as part of a larger cube. So if we look at the solution, we now apply those symmetries and the voltage. Let's just check here the analysis type, new analysis, just a static, so you can do a modal analysis if you want to, look at the natural frequency or harmonic, but we're just going to do a static analysis. We're going to define our loads, we're going to apply our loads. So let's do the symmetry first. So it's a structural displacement, symmetry boundary conditions, and we can do that on the areas. So just on these three areas, areas here. That's good. So on those three areas, I'm going to apply a symmetry. And then remember, I need to then now apply a voltage. And if we apply a voltage, then that thing should expand or contract in response to the electric field. So we're going to apply an electric boundary condition, which is a voltage. And we'll apply that to the nodes. And remember, 1 and 17 were the master nodes of capital list 1 and 2, which was electrodes 1 and 2. So if I just select electrode number 1, on that I'll put a 0 voltage. So that, you can see that turned yellow, so that was at the bottom. And then on number 17, so rather than just doing a box or a selection, I'll just put in the number of the node. I'll put in a voltage of 1. So I've got 1 volt across that. I can always list, sometimes I just double check, list the degree of freedom constraints. So I've got my 1 volt here on 1 and 7 there as well. That's good. So I've got an electric field across it because I've got a potential difference of 1 volt. Across my 1 meter by 1 meter by 1 meter piece of PZT. I've got my properties in, so if I solve it now, it should displace under that potential difference. So I go to solution and solve. So current LS is current load step. Begin solution. It's giving me a warning, but that's really because I've got those magnetic degrees and freedom, and that always comes up, so it's not really a major issue. Yeah, pretty quick, so because it's a very small model. That's good. At least it's solved. The question is, has it worked? So if I look at general post-proc now, which is the post-processing. Plot the results, the deformed shape, so deformed and undeformed shape, and yes, I've got a displacement, so I can see that I've got some piezoelectric strain. It's moved, so Z is in this direction, so it's got thinner, so the field is contracting it. I didn't think too much about the direction of the field where the voltage, so I can either extend or contract depending on the electric field orientation. So in this case it's got shorter, and it's also got wider, because it's a bit like a Poisson's ratio. So I've got as it gets thinner in the polarization direction, it'll get fatter in the X and Y directions normal to the polarization direction. Very good. So let's have a look at the outcome. So if we look at the nodal solution, let's maybe look at the displacement in Z. So here I've got my displacement, so 0 here, and the maximum displacement is a minus. So let's just write that number down. So the strain in the 3 direction, so the strain in or the displacement in the 3 direction, in the Z direction, is 5 minus 0.594 times 10 to the minus 9 meters, which is 594 times 10 to the minus 12 meters. Yeah, so 594 picometers in the Z direction. Let's just have a look in the Y direction. So the maximum displacement, here it's positive because it's got fatter. So in the Y direction, so that's 275 times 10 to the minus 12 meters. So again, that's 275 picometers. And in the X direction, I think it should be the same. Yeah, and then we've got the same displacement in the X direction. And we said that because there's a symmetry in the X and Y compared to the Z. And you can also just out of interest is look at the electric potential, but we know what it should be. We've got a 0 and a 1 because that's exactly what we've applied. So we've got a displacement. That's good, and it seems to work. And we've got a piezoelectric strain. So does the number make sense? Well, let's just have a look at our little structure. So I've just written down the solutions here as I saw them on the screen. So here's our block of material, poled in the Z direction. It has a thickness T and a voltage V across it. So the electric field, in this case, is applied is voltage divided by thickness. So it's 1 volt divided by 1 meter. So electric field is 1 volts per meter. And this is exactly why I did a 1 by 1 by 1 meter block. It just makes everything simple. And for a piezoelectric actuator, the material property in terms of strain is this D33 coefficient. And this for the piezoelectric is the strain per unit electric field in the polarization direction. And the strain is delta T divided by T, deflection divided by initial thickness. Electric field is V over T like this. So I end up with D33 is delta T, deflection divided by voltage. And so my delta T should be D33 times V, where D is this materials property. And as V is 1 volt, then my delta T should be very much equal to D33. So this is the value I've got for this material, PZT5H, and I put it in picometers because I know the D33 is about 600 picometers per volt, and so that's exactly the same as the D33 of the material. So that's in very good agreement with what the D33 of PZT5H actually is. D31 is the strain per unit field in the X and Y direction, and that should again be around 270 picometers per volt, which would then lead to a deflection of 275 or 3 picometers. So again, that's in excellent agreement with the D33. And they're opposite in sign, and that's exactly, again, what you'd expect. If this is positive and this is negative, or this is negative, this is positive in terms of displacement. So that's working extremely well. You might be saying, well, hang on a minute, I didn't enter D33 into the model. But in fact, we did because we input the charge coefficients as the materials properties, and that really is linked to the strain properties as well. So if we just look at the materials properties, materials models, piezoelectric, we input the stress matrix, which links sort of stress and charge, which then is linked to voltage. We could have put in the D matrix directly, so D33 and D31, but I had the stress the E coefficients, but they're in there, and so it's in there indirectly, and so those values are very typical of this material that we put in. So you can choose whether to put in this matrix if you have it, or this matrix for for piezoelectrics, and for the stiffness, if you want, you can also put in compliance as well. So you may have data on the compliance matrix of the material as well. So it's perfect. Seems to have worked first time as well. So that's good news. So I'll finish there.